Welcome to another webinar as part of our summer training program for the computer engineering students at KFUPM. Today's webinar is a primer on machine learning, and it will be given by Dr. Ibraheem Alabdolmohssin. He is a research scientist in Google Brain in Zurich, Switzerland. Before joining Google, Dr. Ibraheem was the lead of the advanced analytics team at Saudi Aramco here in Bahrain. Dr. Ibraheem is also a member of the advisory committee for this summer training course, and he will be mentoring our students in their projects. Before I turn it over to Dr. Ibraheem, I would like to mention something for those who are watching us on YouTube. You can post your question into the chat area at any time, and I will try my best to ask these questions at the end of the session. We also have with us in the meeting room the students of the summer training program, who will be given a chance at the end to interact with Dr. Ibraheem. تفضل دكتور إبراهيم.
شكرا Dr. Yahya. Before I begin my talk today, I'd like to highlight a few important points. So first, a disclaimer. So my talk today is meant to provide a quick start introduction to machine learning. So the intended audience are undergraduate students with no formal training in machine learning, but want to use machine learning in their projects. So a few weeks ago, I had the opportunity to chat with some of those students at KFUPM. My hope is that by the end of this talk, they will understand the machine learning workflow and how to verify or validate machine learning models. So if you are already experienced in this field or have completed a course successfully in the past, you may not find most of the contents useful, except perhaps the last part, in which I discuss some good rules of thumb. I wanted to mention this first, just to set the expectations right. Okay. So second, and I believe this is very important, machine learning is a very broad discipline. So please do not assume familiarity with the topic by only understanding the concepts presented here. These are bare minimum, but they are not enough. So it's important to continue to read, study, and practice. So tentatively, the plan was to have 45 minutes for the talk, plus 30 to 45 minutes for discussion, depending on how much time we have. So please ask as many questions as you want. I think this second part will be more important than the first, because admittedly, there are many webinars, courses, or talks that cover machine learning on the web. I hope that, or I expect that the students would benefit more from the discussion. In any case, as I mentioned, the times here are tentative. Please feel free to interrupt me if you have any questions. Do not wait until the end. Okay. So this is the outline of the talk. I'll first begin with a brief introduction to machine learning, what it means and how it is used in both science and engineering. Then we'll walk through an example in detail. We'll see how a problem can be formulated as a machine learning problem and how it is solved under the hood. Third, we will go through the machine learning workflow. Here, we will discuss some important basic concepts that anyone using machine learning should be familiar with, such as hyperparameters, model selection, cross-validation, and overfitting. And finally, I will present a few rules of thumb that I find to be useful in practice when building machine learning applications. My hope is that you will find them useful too. Okay, so let's begin by introducing machine learning. So often one of the best ways to understand a new concept is to place it in its historical context. So how does it relate to previous ideas? What does it solve, and how did it evolve afterwards? For machine learning, if you are currently considering the use of this field, you probably have a problem in mind that you want to solve, and you are wondering if machine learning is the right way to solve it. Now, to answer this question, let us see first how you would have solved this problem in the past without machine learning. This would help us understand why machine learning was developed. So until a few decades ago, if you were confronted with a scientific or engineering challenge, we would tend to tackle it using one of three paradigms. So the first paradigm or approach is rationalism, which answers questions by reasoning theoretically, such as using mathematics or logic. So for example, if you want to know the relationship between certain geometrical shapes, you can derive theorems analytically. The second paradigm is empiricism, which answers questions by collecting empirical evidence, such as from observations or experiments. So for example, if you want to know the composition of the atmosphere on a distant planet, you can collect observations such as the spectrum of the light received from that planet and infer the composition from that spectrum. This is an empirical approach. We don't reason about the atmosphere. We just provide empirical evidence that answers the question. The third approach is computational methods, namely coding. So one common example is simulation. So for example, let's say you have a dynamical system and you want to understand how this dynamical system behaves. Instead of deriving theorems analytically or going outside to collect field measurements, what you can do is you can simulate the dynamical system and observe how the system behaves. So this is a computational approach for discovery. Okay, so these are three classical ways for solving problems or for tackling challenges in science and engineering, but they're not always sufficient. In some cases, and I will give concrete examples shortly, it would be extremely difficult to solve a problem using any of these classical approaches. Instead, what we do is we have plenty of data, and the best way to solve a problem is to build a system that can learn from that data. So if you are in this position, you'll probably be using machine learning to solve your problem. So when properly interpreted, machine learning might be viewed as another paradigm for solving challenges in science and engineering. It is not just another computer science subject. And I think this is very important to highlight. Before I move on to the next slide, I want just to highlight, of course, an obvious fact. These different paradigms are not mutually exclusive. There are sometimes the situations where you would benefit from using all of these four paradigms together. For example, reservoir simulations today, they can be based on mathematical models, such as finite difference methods, and physical laws, such as rock properties, apply to empirical measurements, such as sensory data, and enhance accelerated using machine learning. So you can use all of them essentially to tackle an engineering or a scientific challenge. Okay. So let me give you one example of how the analysis of existing data has been used to solve a problem in medicine. I earlier mentioned, or I made the claim, that data analytics is a new paradigm for discovery. So let me give you an example in medicine that illustrates this fact. So the example is about a special type of antibiotics that are used to prevent infections during medical surgeries. They are commonly used today, but they were not widespread in the past. And the reason why they were not that common in the past is because there was not a conclusive evidence yet. Since 1965, there have been over 30 studies that looked into the effect of these antibiotics. And almost all of the 30 plus studies that spanned over 25 years were inconclusive, as I mentioned earlier, due to the large error bars they observed. So those antibiotics were not commonly used during that time. However, around 1990, a group of scientists carried out what is called meta-analysis, which combines the available data in previous publications and analyzes them. They found that the benefit of these antibiotics was in fact statistically significant. So after that, they became a standard practice in medicine today. So essentially, we're talking about a new medical discovery that was achieved purely by the analysis of existing data. No new reasoning was introduced, no new experiments were conducted, just by the analysis of data. And you can only imagine today, with the explosive growth of the data and the World Wide Web, how much impact this approach could potentially have to our lives in the future. So this is one example in medicine. In engineering, there are many other examples. Data analytics or machine learning has been used to solve challenging problems, including spam detection, image classification, recommendation systems, such as what you see in Amazon and Netflix, machine translation, financial fraud detections. There are many commercial solutions for this, and predictive maintenance, which has made a big impact in many industries, including oil and gas. So the general principle in these applications is that we have some unknown function f that maps input to output this function can be quite complex, but we have plenty of examples that come in pairs of the form x and f of x. And these examples reveal some information about the underlying function f. So instead of reasoning about f analytically or rationally, and then hard coding an approximation to f, what we can do instead is to let the machine learn this function f based on the available data. This is an objective approach, it's precise, and can be made more accurate by gathering more data if needed. In addition, in many cases, in practice, this function f has some useful structure, for example, smoothness, which makes machine learning-based approaches more efficient. So this is essentially the main advantage of using machine learning. Okay. However, it's important to keep in mind that machine learning is just another tool for solving problems. It is not a goal by itself. And the reason I'm saying this is because you will sometimes hear of applications of machine learning that use complicated approaches for the sake of using machine learning when simpler approaches suffice. Please do not do that. If there is a simple way to solve the problem, go for it. Do not use machine learning for the sake of using machine learning. Okay, so let's take a detailed walkthrough example to see how machine learning works under the hood. So I'm going to use a very simple example with a very simple machine learning algorithm to illustrate, in order to illustrate the main idea. Of course, modern applications today, they can be much more involved. Okay, so the example I'm going to use today is email classification. So suppose you are an email service provider and you would like to classify emails into either spams or non-spams. How would you do that? In the 1990s, the way some internet companies used to do this was to gather experts who were brought together and asked about their opinions. So they will ask the experts, for example, to propose techniques for detecting spams and then try to implement those techniques in the spam filter. Of course, the experts might, for example, the experts might suggest looking for certain keywords, misspellings, embedded links, and so on. Now, unfortunately, this approach did not work quite well. Maybe some of you remember, at least the old ones, my generation. Some of you might remember how spams were a source of annoyance around 1999 when the internet was first introduced into the kingdom. Now, why didn't this approach work well? And there are at least 3 reasons, and I'm sure you can think of more. So first, the approach is very subjective. It is based on the opinions of experts who might even disagree. And second, it is a fixed approach. It is non-adaptive, whereas spammers are known to change their tactics regularly. So this approach could not adapt easily. And third, it is imprecise. For example, it does not give us a meaningful way of assigning weight to rules. How do we know which rule is more important than the other? So now let's see how machine learning fixes these issues. Okay, so basically one way to use machine learning is to let the machine decide on the questions for which we do not have an answer known in advance. So for example, we can still talk to experts, ask them about how they think or what they think would be important in detecting spams. And they might suggest looking for certain keywords, for example, the word special offer or buy and so on. However, instead of using those particular keywords or assigning some arbitrary weight to them, which would be imprecise and subjective, we can let the machine build a dictionary of words based on the data set that we have, based on the corpus of emails, and then learn the importance of each word automatically. So how do we do that? So one way is to scan through all of the emails we have in the dataset and extract all of the words to form a dictionary, such as the one shown in the table here. So here the table has only 5 words, but in practice, if you were to implement this, you would have maybe tens of thousands of words in the dictionary. Then, once you build your dictionary, for a given email, you count the number of occurrences of a particular word. In this example, shown here in the table, the word boy occurs 2 times in the email. The word cat happens to occur 0 times, and so on. So you record the number of occurrences of every word. Now, besides keywords, the experts might also suggest additional features, such as the number of misspellings, embedded links, and so on. For every feature, we transform it also into a numeric score. Okay? And once you decide how to transform an email into a numeric vector in some very high dimensional space, you label every email manually. With this, an email reduces to a point in some high dimensional space, as shown in the figure on the right. So you have some high dimensional space with a very large dimension, and every email is represented as a point in this high dimensional space. Next comes the learning part. In this case, you might want to, or you might try to find a hyperplane that separates the spams from the non-spams. For example, in 2 dimensions, this would be a line as shown in the figure. And this is where the machine learning algorithms come into the picture. They find that separating hyperplane for you. For example, support vector machines or logistic regressions. However, please know that you still have to do a lot of work before you reach the stage where we could use those algorithms. Okay. In addition, if you are a bit careful, you might realize that there might be different objective functions that we want to optimize. For example, if you are interested just in minimizing the misclassification error rate, you would get something like the line showing on the right, the dotted line showing on the right in the figure. Okay, this is fine if you want to minimize the misclassification error rate. However, for spam filtering, this means that a lot of non-spams shown in blue would be classified as spams, and they will be automatically sent to the spam folder, which is something that is not desirable. So in this particular case, what you want to do is you might want to assign different penalties for misclassification. And again, this is one of the design issues that you should keep in mind. Okay. So what are some of the immediate advantages of this approach? First, it is objective. So maybe the only subjective part here is the choice of the features, but it's not problematic for this type of applications. For other applications, yes, this could be an issue. There is a growing field of research called the presentation learning, but it may not be that particularly important here. And second, it is adaptive. Okay, so you can adapt to the changing tactics used by the spammers by refreshing your data set and retraining the model every once in a while. And it is precise. For every feature, for every rule, the model will assign a weight based on the data, so you will know which rule is more important than the other. And it is easy to implement and works quite well in practice. Okay, here's a sample pseudocode in Python on how to do this. So suppose data here contains all of the emails in your data set. So the first thing that, as I mentioned earlier, the first thing you would need to do is to build the dictionary. And you can be here a bit more sophisticated. So you don't just count words, you don't just take words as is, you can apply more processing into the word. For example, stemming, stop word elimination, and so on. So you can be sophisticated in this procedure. And once you learn the dictionary and fix it, then you transform the data, the emails, into numeric vectors, as I mentioned earlier. The dimensionality of the data will be equal to the size of your dictionary, so it can be very large. However, note that in this particular case, most of the entries will be 0. So your matrix, your data matrix, will be quite sparse, which is something you should exploit to accelerate training. So there are packages for sparse linear algebra that you might benefit from. And finally, you can just import the algorithm of choice that you want, SVM, logistic regression, and so on, train the model, and finally predict. Okay, I'm going to pause now in case anyone has any questions. So before I proceed to the next, if you have any questions, please let me know.
Okay, Shabab, if you have any question, please raise your hand. Okay, it seems that we don't have any question and they're all happy about the introduction.
Okay, so if no one has any questions, let's proceed. I just described how to build the machine learning model, However, this leaves another important question unanswered. How do we verify that a model works as intended? Now, this brings us to the subject of the machine learning workflow. Now, why is this important? Why do we need to worry about verifying correctness? So one way to see this is to look into the scientific method. The scientific method proceeds in stages. We first collect observations and build a hypothesis or a model based on those observations. However, the core of the scientific method is that we do not stop there. You don't just hypothesize an explanation that fits the data, because anyone can do that. Instead, you have to make predictions based on your models and test those predictions using new data. So those predictions have to be also falsifiable. They have to be refutable. Okay? A similar approach in machine learning is used today. In machine learning, there are two approaches for verifying that the machine learning model works as intended. So we will generally be concerned with the first approach, but I will also mention the second approach for completeness. So the first approach is to reveal the test data only after you select the model, and then you test the model on that particular data set. Now, this is similar to the way you would test students' understanding of a subject. You don't just reveal the exam questions before they study, because then they can just focus on the test questions. The same thing happens in machine learning. So you don't want the machine learning model to see the test data before you train the model. And it's important, this is extremely important. So you only see the test data after the model has been selected. There's also a second approach, but as I mentioned earlier, this is not very important. The second, but I will just mention it here for completeness. So the second approach is to fix a small set of candidate models in advance before you see the training data, not the test data. Then you can use your training error as an estimator to the performance. This may seem quite strange. Why would you use a training error? But it's actually well-founded. There is an entire field called statistical learning theory that looks into this. However, as I mentioned, most people, they just use the first approach, which I think you should do that too. Okay. However, this
Dr.
is not
Ibrahim,
the yes.
Can you go back and explain the prediction have to be falsifiable, otherwise they are void? I don't think they got that one.
Okay, so this is more general to, so in the scientific method, if you want to validate a particular model, you would have to come up with predictions. And those predictions, when I say falsifiable, they have to be falsifiable. But when I say falsifiable, that means that they can be disproved. They're not tautological, for example. Let me give you an example. In physics, string theory, there are many people who are excited about string theory in physics, right? However, there are many people who believe that string theory should not yet be viewed as a branch of physics, but more of a branch of philosophy. And the reason that they do this is not because string theory is not sound or because it does not describe observations. The main reason they do this is because string theory does not yet make predictions that can be tested, verified, or disproved using the technology that we have today. So it's very important to make predictions that can be disproved. In machine learning, the way we do this is to have a test data. This test data is already labeled. So we know what is the correct answer for every example on that test data. But we don't show this test data to the model. Once you train the model, then you test the model on that test data. So you reveal the examples one by one, and you see what the model predicts and compare the prediction to the true answer. So in that case, if you are not really learning anything useful, you will observe this on the test data. You will see that the performance of the model is very poor in the test data. So this is falsifiable.
There is a question that related to the second approach in ML. Somebody is saying he did not get it also.
Okay, so the second approach, basically, in statistical learning theory, okay, there's one of the big branches of that particular field is to say, when is my performance on the training data a good approximation to my performance on the test data? So this is, and the reason why we are concerned with this is because we are building a model based on the training data. If we can find conditions that will make the training error a good approximation to the test error, then we will have a good machine learning model because we are optimizing the training error. Okay? Now, what happens is there are many conditions that have been established in the literature for doing this. In general, the general idea is if the set of hypotheses or models that you are willing to consider in advance is very small. So let's say you are considering a few classifiers only. You're not considering many classifiers. In that case, you can show that, yes, your performance on the training data will be a good approximation to the test error rate. This would be okay, would be useful, as I mentioned earlier, if you have very few classifiers or your classifier satisfies some certain conditions. It's rarely the case that people use this in practice. Okay, so I would not recommend that you worry about this, except if you don't have a lot of data to begin with. If you, in your case, if you have a particular application where you cannot afford to have a test data, you just want to build a model based on the entire data because the data is small anyways, then we would worry about this approach. But in that case, let me know. We can talk about this, how to do this properly. Okay. But if you have plenty of data, don't worry about it. Use the first approach. Okay.
Okay.
Okay, so I just mentioned that we need test data and training data. Unfortunately, this is not the full picture. It's a bit more elaborate than this. So in machine learning, the standard approach is to split the data set into 3 disjoint subsets, not just 2. These are called the training data, the validation data, and the test data. Why do we do this? So we know that the training data is used to build the model. So for example, the linear classifier I mentioned earlier in the case of spam filters. So you have a training data and you choose the linear classifier based on that training data. However, in many cases, often you will find yourself faced with many design choices that you need to choose from. For example, which algorithm to choose. You don't need to stick to a particular algorithm. So you have many algorithms to choose from. Or which loss function to choose. As I mentioned earlier, you might be interested in assigning different penalties to the misclassification error rate. So these are decided based on the validation data. So the validation data is used to choose among those options, which are called, in the literature, they are called hyperparameters. So let me give you an example. Okay, so suppose you want to decide which algorithm to use. You are considering support vector machines, random forest, and the neural networks. So the way that you would choose one algorithm over the others is to train all of them in parallel on the training data set. So the same training data, you train all of them on that particular data set. Then you measure their performance on the validation data. And you pick the one that seems to work best on the validation data. You don't use the test data set because the test data set should only be used once. At the end, once you're done with your analysis, once you choose your model, you use the test data set to report the accuracy. You never use it twice. Okay, and this is extremely important. Okay, so this is usually the way it's done. You have this 3 split of the data. However, in some cases, data might be scarce. You may not have plenty of data, and you cannot afford to have a separate validation data set. In that case, there is other techniques that you can use. There's something called k-fold cross-validation. I mentioned it here in the slide. So the idea here is to take the training data set. If you look down, you will see in the figure in the middle. So suppose that this is your entire training data set. You can split it, for example, into 4 subsets. This is the same training data set. You split it into 4 subsets. You train based on 3 subsets of the training data, and you measure the accuracy on the remaining subset. This is the remaining subset, the one shown in dark gray. And then you repeat this. So you choose now another subset. You train on the 3, and you test on 1, and you train on 3, and you keep doing this multiple times. And then you take the average performance on that particular subset that you left out at every time. This is called k-fold cross-validation. This is one way to do this if you cannot afford to have a separate validation data set, because you don't have plenty of data to begin with. And the idea here is you do something, so you are making full use of the training data, when doing this validation. There are also, in some cases, you might even be the data might even be more scarce. So, for example, let's say take a hypothetical scenario. Let's suppose that you have 100 examples only. That's all you have, but you have 50 dimensions. So you have a very limited data set. In that case, you may not even afford to go with k-fold cross-validation. So what you can do is you take an extreme case. You go with what's called leave one out validation method, which is an extreme form of k-fold validation. In this case, you leave one example out. You train on all of the remaining training data set. You leave only one example out, and you test the performance on that remaining example. And then you repeat this for every training example, and you take the average performance. This is well motivated. There is theoretical basis for this, but it is computationally expensive. So you should only do this if the data is very limited, if you have issues with the data, with the quantity of the data. Okay. And once you're satisfied, so this is the training and the validations. Once you're satisfied, once you choose your model and you're done with the analysis, then you use the test data. You report the accuracy on the test data. But as I mentioned earlier, the test data should ideally be used only once. It should not in any way change the model or have an impact on the model. So keep this in mind. There are many people, some people, they might think that since I'm not using the test data to build the model, I will not have overfitting on the test data set. But this is actually wrong. You can overfit on the test data set if you are going to keep repeating the whole process over and over again until you get good performance on the test data. You should not be doing that. The test data, think of it as just a way to report your accuracy at the end. Do not use it more than once. Okay, is this clear or?
Okay, Shabab, I think this slide is very important, especially that you have been attending other online courses. And I can tell from your report and from my communication with you, you are not used to this new concept of validation. You only know training and testing. So before we move on to the next slide, we want to make sure that you are getting this new concept of validation. Please raise your hand if you have any question. So Dr. Ibrahim, we're going to have an example at the end, a concrete example that will show us how do we deal with the data, like how do we split it into 3 groups?
No, this is what I had in mind. So if yeah, so as I mentioned, yeah, this is so you take the data, you split it into 3 subsets. I didn't have a slide specific in how to do that. I mean, this is.
Let's say that we have a data set with let's say 10,000 entries. How do we go about this training and validation?
Okay, so let's suppose you have, yes, as you mentioned, I have 10,000 images, and I want to classify these images into 10 classes, for example. So in this case, usually what happens is you can reserve 60% of the data set for training. That will be 6,000 images. Choosing at random. Of course, it's very important to randomize. You have 6,000 examples for training, 2,000 for validation, and 2,000 for testing. The testing data set, we put it aside. We are not going to see it until the very end when we're done with everything and we just want to report the accuracy. So ignore the test data set. Now you have only 6,000 examples for training and 2,000 examples for validation. Now the way you would do this is within the machine learning model, there are certain parameters that you can play with. Okay, for example, there are what's called there is penalty parameters for the regularization. Sometimes the choice of the algorithm that you want to use. There are many algorithms that you want to try. The point is that when faced with these different options, try all of them in parallel on the training data, on the 6,000 examples, and measure their accuracy on the validation data, which is the 2,000 images. And then you pick the one that seems to work best on the validation data. Once you're done, once you are happy with your performance and you're ready to report the accuracy, then you can use the test data to report the accuracy of the model. In some cases, usually you might find that no, none of them works best on the validation data. So I need to try different algorithms. That's fine. But the test data, keep it aside. Don't use it. So you still have that training data. You still have that validation data. Try now different ways, different techniques, pre-processing. Maybe you want to pre-process the images. Do whatever you want to get the good performance in the validation data. But don't touch the test data set. And once you're done,
so the validation phase, like in the training phase, it's about collecting features and building the model. The validation phase is about judging the performance of the different algorithms that I'm going to use.
Of it. Yes, because eventually you want. You can think of this. You can think of it this way: is that you will because eventually you want to choose one algorithm, right? Yeah. So if you choose based on the test data, that will be a biased estimate. It's not gonna to not give you a reliable estimate of your performance later. If you do it based on the validation data, you're fine, because eventually you will be reporting the accuracy based on the test data, not based on the validation data. So you use your validation, you use your, as you mentioned, you use the validation data to choose which algorithm works best. But then once before you make a claim that I could reach 95% accuracy, you don't do that based on your training error or based on the validation error. You do that based on the test error.
Okay, so you do not commit to a specific algorithm early on, before you start the ML project, because some students they have already made up their mind on which algorithm they are going to use.
Okay,
they have
I will
to
talk
wait
about this. Yeah,
okay.
I have a slide on this. I'll talk about this.
Okay, fine. One quick question before we leave this slide. Is there a rule of thumb that I can use to tell if my data set is small?
Yeah, usually a good rule of thumb is to compare the number of examples with the dimensionality of the data. Okay, I'm talking about, since this usually works for tabular data. The data can be written as a table, not as an image, for example. If you're going to be using tabular data, usually the number of examples should be at least 10 times the dimension of the problem, the number of dimensions.
Okay.
But of course, it depends. Now, it all depends on the algorithm that you're going to be using. If you have an issue, let's say that the number of examples is very small compared to the problem dimension, you should use simpler algorithms that tend not to overfit. For example, you should use linear methods. But if you have plenty of data, if the data is huge compared to the problem dimension, you can use non-linear, non-parametric methods. So that would be. So you need to worry about this. You need to take this into account. Usually, if you follow this procedure that I just mentioned, you will see that something is wrong. That okay, I use a very complicated algorithm when I had issues with the number of examples and the number. You will see that my performance in the validation data is not doing well. So you will know that there is something wrong.
Okay.
Yeah, but this is a good rule of thumb. At least the size of the data set for tabular data, the size of the data set should be at least 10 times the problem dimension. If it is small, if the number of examples is very small, go for simpler algorithms like linear methods. But if you have plenty of data compared to the dimension, you can go with more. You can go for more complicated approaches. But this does not work for images. It's a bit more. The situation is a bit more complicated for images. For images, you are using convolutions. This effectively increases the effective number, essentially, of examples. I don't want to get to this now. If anyone's
Actually,
going
they
to be
had
using...
a webinar last night with Dr. Ibraheem Alhashim
Okay.
on neural networks and deep learning for dealing with images and videos.
Good. Yeah. Okay. Yeah.
Okay.
Okay. Should we move on to the next slide?
Yes.
Or, okay, so why are we doing all of this? Why do we have this three splits of the data? Okay, why do we have this very somewhat elaborate process? And the reason comes from a fundamental trade-off in learning. So essentially what we want to do is, we want to, if you think about it, we want to learn from data, but at the same time, we don't want to be overly dependent on the data, which is a bit of a contradiction. How do you learn from data without being overly dependent on the data? So consider that, to see this, consider the example shown in the figure on the right. So let's suppose that you have these, the points marked as circles in the figure, and you want to predict the y value giving the value of x. Now, if you give yourself enough freedom, you can come up with a wiggly curve shown in green. This may give you the impression that you're doing extremely well because you fit the training data almost perfectly. However, it will tend not to generalize. It will not work well if you reveal a new subset of the data. So in the test data set, it will not work well. On the other hand, so this is because the model is very complex, and we call this phenomenon, we call it basically overfitting. Overfitting simply means that you have focused too much on the training data, even though your real interest is in the future data that you have not observed yet. Okay, so this is overfitting. That's one extreme. At the other extreme, if you restrict yourself to a simple model, an extremely simple model, like the linear function, the line shown in blue, yes, this model is, and you train it based on the data, this model is almost independent of the examples. That's a good thing. But at the same time, you cannot fit the training data. You're not really learning from the training examples. So this is another way to fail to learn from data. And we call this underfitting. So you have these two extremes. You have underfitting on one hand and overfitting on the other hand. And what you would want to do is you want to strike a balance. You want to use a model that is not too simple and it is not too complicated. And the way to do this is to look into the validation data. So you try different approaches, you try different models, and you measure the performance on the validation data, and you choose the one that seems to be working best on the validation data. This will tend to strike a balance between underfitting and overfitting. Okay. Okay, so I'll next give a few rules of thumb that I think are very useful to keep in mind when running machine learning projects. I hope you will find them useful too. Okay, so first is the data quality. In general, in practice, practitioners usually they expect to spend about 50 to 70% of your time on preparing the data. Do not be frustrated by this. If you find yourself in that position in your projects, do not be frustrated by this. Some of the things that you should keep in mind are which data to collect, how to fetch it, what pre-processing steps would be needed. For example, imputation, normalization, feature selection, outlier removal, and so on. So there is many things that you can do as a pre-processing step before you start to train the model. Now, I know I just throw in a few terms. Do not be intimidated by them. These are actually quite simple concepts. If you just go look them up, you will understand them very quickly. And they're usually implemented, available in standard packages like scikit-learn in Python. You find them already implemented, so you can just use them right away. Okay. So data quality, I just want to highlight data quality. Now, why do we do this? We do this to improve data quality. And data quality is very important. Do not think of this as the low priority task. So before you spend too much time on fine-tuning the model, try to identify ways to improve the quality of the data first. But please do this with caution. You don't want to change the data significantly that your future, that the data in the future becomes quite different from your training data set. In this case, you will fail to predict in the future. So do this with caution, but it is a very important thing to keep in mind. Data quality is extremely important. In addition, it is usual customary to revisit the scope of the project based on the data you have. Now, ideally, in an ideal situation, one would hope for the pipeline shown at the top, where okay, you start from the scope, you finalize the scope, then you go and collect the data, and then you finally build the model afterwards. But this is rarely the case in practice. In many cases, you might change the scope based on the availability of the data, or even based on the results of the model. In some cases, you might change the data based on the model results, but not the scope, and so on. So the point I want to say is you might find that in your projects that you will need to develop all of them together in parallel, both the scope, the data, and the model, not in sequence. Again, if you find yourself in that position, do not be frustrated. And this is sometimes expected. Okay. So data quality. So the main takeaway is pay attention to the quality of the data. This is very important. Second, there is a famous theorem in machine learning which says that no free lunch exists. Dr. Yahya, he tweeted about it recently.
Thank you.
So the basic idea is that there is no single algorithm that works best universally. So you should try multiple algorithms. So one example is, just to give you an example, is an optical digit recognition, where the goal is to recognize handwritten digits, as shown here in the right. So in this application, if you start with a linear classifier, you will get about 92% accuracy, which might be okay, acceptable depending on the application. However, if you try nearest neighbor classifiers, which is another very simple algorithm, you would get 97% accuracy, which is a big jump compared to linear classifiers. You can still do much better than that using deep neural networks, which gives state-of-the-art results in this problem, exceeding, you'll get more than 99.7% accuracy. So try multiple algorithms. Do not stick to one particular algorithm in advance. And I think this is something that you, Dr. Yahya, you just mentioned a few minutes ago, that some students, they already have a certain algorithm in mind for their application. I don't think that's a good idea. Try multiple algorithms. But of course, these algorithms should be diverse. I mean, if you, for example, if you're wondering whether you should use logistic regression or linear SVM, I wouldn't really worry that much about it. They would almost give you the same result. Yeah, so don't. But you should try different algorithms, like nearest neighbor classifiers. This is an entirely different approach from linear methods, which is an entirely different approach from random forests and neural networks and so on. So try these different algorithms. It's always good. You will not lose much by doing this. Okay. Third is often one of the best ways to improve performance is not to implement sophisticated models, but simply to gather more data. This is often the quickest way to improve performance in your application. You should try this first if it is easy, if there is a way to gather more data. And don't worry about the impact on the training time. You know, there is a general misconception that if I gather more data, training would take longer time. But in machine learning, this is not the case. In fact, more data speeds up the training time. Now, I don't know, can anyone think of why this is the case? I mean, just reading the data would take longer time. If I have more data, just to read it, I would take a longer time. But I am, at the same time, I'm making a claim that training in machine learning would be faster if you have more data. Can anyone think of a reason why?
Okay, Shabab, raise your hand if you have an answer.
I know it's not intuitive. I'm saying even within machine learning practitioners, they often don't they don't know this fact. So, but the reason is very simple actually. The reason that in machine learning, what we care about is accuracy, not convergence. So if your goal is to get 90% accuracy in a particular application, like optical digit recognition, when I mentioned earlier, you will often do this faster if you have more data. And the reason why is because with more data becomes a better representation of the underlying distribution. So you will be able to get a better test accuracy quickly if you have more examples. Then you can stop. You don't have to keep training until convergence in machine learning, because you don't need to. If you train until convergence, you are basically more interested in the training data set. But the training data is just a proxy for the underlying distribution. I'm not really concerned with the training data. I'm just using it as a proxy. So that's why you can stop early once you reach the level of accuracy that you desire. And often, if you have more data, you will reach that level of accuracy fast.
Dr. Ibrahim, can you define what you mean by sophisticated model?
Yeah. So as I mentioned, okay. So let's suppose that you have an application and you try a linear classifier. Linear classifier is a very simple algorithm, and you find that a linear classifier does not give you a very good test accuracy. It might be the case that before you go to more involved approach, like kernel-based methods, or you go to neural networks or random forest, or you try to tweak the hyperparameters, and you keep doing a lot of things just to, or you pre-process the data. You spend a lot of time in pre-processing the data and doing a lot of work just to get the test accuracy to improve. If it is easy to get more data, try that first. You should spend more time in getting that first, because that's often the quickest way to improve your performance.
Okay.
Yeah, but then I understand that this is usually it's getting more data is the difficult part. But I'm saying
There is
yeah.
there is an interesting question from Khatem. Can data augmentation help improve the performance
Yes,
better than
yes,
finding new data?
yeah, of course, yes, of course. Data augmentation is one of the golden rules of thumb. But this is usually for data such as images. You don't. It's difficult to come up with data augmentation ways for tabular data. But yes, if you are going to use images, data augmentation is extremely important.
Okay.
It will, yeah. So if you use like a simplified convolutional neural nets, the accuracy can jump significantly if you use augmentation in the image. Augmentation is one of the golden rules of thumb that you should use.
Okay.
Okay. So my main point here, the one maybe sentence takeaway message is try to get more data if you can. If it is easy, do this. This is often the best way to improve your accuracy. Okay.
Okay.
And fourth is yeah. So fourth, it's important to keep in mind that what the model learns depends on the distribution of the data, which is sometimes not what you would expect. So what when I say here not what you would expect, I mean what the model learns is not what you would expect yourself. Let me just give you an example. Let's suppose that you have images of this 7-segment display. I'm sure you remember 7-segment display. Probably in digital logic, you've done something. You've done some work. So with the 7-segment display, so you have 7 segments. You represent every digit by 7 segments. Okay? And let's suppose that you now have images, noisy images of these 7-segment displays, and you want to train a classifier, a linear classifier that recognizes every image. So I give it images. Let's say, for example, I want a classifier that will recognize the top segment. Let's call it segment A. Okay? And I give it images of digits labeled. So for digit 0, I would say, yes, the segment is there in the digit 0, but not in digit 1. And it is there in digit 2 and 3, but not 4, and so on. So you give it a lot of examples. And now you want to build a machine learning model that can recognize the image. If you train this model on even numbers, just as an example, what you will observe is that the model will think that the top segment or segment A is actually this segment here, which is the correct one, in addition to these 2 segments. So the whole thing, these 3 segments together, they define segment A. So it's not really just the top segment that as you would expect. If you go with segment B, you will find that it will learn that these 2 together are segment B, not the first one only, and so on. And the reason why this happens is it depends on the distribution of the data. If I'm always showing the model even numbers, for even numbers, whenever the segment A happens, is true, these 2 segments will also be true. So the model cannot distinguish between them. It will just learn that, yes, all of these 3 together, they form the segment A. And this depends on the distribution of the data that you have. So yes, you keep the distribution of the data in mind. Now, usually in your case, what would happen, the way that you would take this into account is make sure that your future, when you think of deploying the application or testing the application, make sure that in the future data will continue to be similar to the past, the training data that you used to build the model. So this is very important. To always think of this in mind whenever you build whenever you build an application. Is my training data that I use to build a model a good approximation to the data that I expect to receive in the future when I deploy the application or when I test the application? This is something
But
very important.
I'm always under the impression that if I have a clear design for my data set, like these are the feature I need, I should not run into this problem of mismatch between the current and the future data.
Yeah.
Is that
So
right?
one example, because the distribution of data sometimes changes. Let me give you an example. Let's suppose you want to build a spam detector. Okay, so you take a sample of emails. The spammers, they use certain tactics. For example, they might replace some of the letters within the word with a number that's like L with with digit 1. It's not visible to the human eye. It will not, the reader will not see the difference. But for a machine, it's a different character entirely. Okay, these tactics, they change over time. So yeah, so you don't. So if you build a model, you should take this into account. That in the future, I might need to refresh my data sets and retrain the model because things have changed over time. Or another example would be: let's suppose that I want to build an image classifier. I want to recognize images of animals. I might go ahead and take the images myself. Okay, I'll take photos of cats and dogs and birds and build a classifier. But my intent is to deploy this classifier on images that are available in the web. These images available in the web, they don't come from the same distribution as the ones that I used in the training data. They're not images that I took myself, which might be different. So you need to take that into account.
Yeah, so this concept is very interesting. This is how you can also do attacks on ML models by injecting data
In the attacks,
that is from a different distribution.
yeah, the attacks, so you're referring to adversarial examples. So what happens is in deep neural networks, if you take an image, and the model is very confident in its prediction about the image, what you will find is that I can add a very little noise to the image and change the predictions of the model significantly, even though for us, for the human eyes, we don't perceive the change. So the image almost appears to be the same as before. Yeah. Yeah, but not for the model. For the model, the predictions will be completely different if you make those attacks. So yes, in that case, those attacks, they change the distribution of the data. So you're right in that. Yes, so that's one of the ways to actually to mitigate that risk is to simulate those attacks during the training data sets. So to make the model more robust against those types of attacks.
Okay.
And the fifth point I want to mention is you should always exploit the structure of the problem. So, for example, if you want to have a linear classifier, you should use packages that are specifically written for linear methods, like liblinear, Pegasus, and SVM-perf. Do not use a general purpose like SVM or a solver, support vector machine solver. And the savings can be quite significant. They can reduce the complexity from quadratic complexity to linear complexity. So this is very important. You should always take this into account. For SVM, as another example, if you want to use support vector machines, there is specialized packages in SVM, such as libSVM, that you should use. Do not use the general purpose QP or quadratic programming solver. The savings can be significant. If you want to go with deep neural networks, use frameworks for deep neural networks like TensorFlow and JAX. Okay, so take the structure of the problem into account. This will save you a lot of time. And finally, please, before you begin your machine learning workflow, please do not forget to randomize before you start. Make sure that the data is appropriately shuffled And the data splits that I mentioned earlier are at random before you begin your experiment. This is very important. Do not assume that the data is already shuffled for you. In many cases, we download the data set like from the UCI repository. They may not be shuffled. Don't forget to shuffle the data set. Okay. Thank you.
Thank you, Dr. Ibrahim, for a very interesting and useful presentation. And now we open the floor for questions from the students. Also, those who are watching us on YouTube, please go ahead and post your question into the chat area. Okay, Shabab, if you have any question, raise your hand. We have an interesting project with Abdullah Sheikh, Ye, and Shehri. I read their report, but they are insisting on using a special algorithm. So if Ye is around, Ye, can you go ahead and tell us why did you decide on random forest for your problem?
Hello, can you hear me?
Yes, raise your voice, please.
Hello?
Yes, I can hear you.
We searched through the literature, and the different algorithms that came up was multivariate linear regression, support vector machine, random forest, and the last one was naive Bayes. And from what we read, in the particular situation when they're categorizing the cars, they kept saying that random forest would branch out because it's a massive group of decision trees. It would branch out all the features of the cars into these different decisions, and it would choose according to whatever weights that we gave to these features, which we would get from a regression, a linear regression, and they would choose. The thing is, they in the literature that we saw, they tried the different methods, and random forest was the best. The thing is, they also tried support vector machines, but they always got some weird result, and they would always say that their actual percentage of accuracy would never exceed 50%. And yet it's either when they did it with random forest, or they did all three of the different algorithms I just stated, they would get 80, 85 or higher.
Okay. Yeah. So what is so your data in this case is a tabular data. It's not images, of course, right? So
yes, it's tabular data.
Yeah. Okay. Yeah. So the one thing to keep in mind, I wanted to mention this maybe, but I did not do that. So if you go back, and this is probably the reason why SVM did not work. Let me go back to the slide. Yeah, here. So as I mentioned, usually this is one way. If you want to build if you want to try a linear method, a linear classifier, or like SVM, you would convert your data scores, right? So one way to do that, it has to, in order to do that, this conversion into scores has to be meaningful. Of course, there is some ordinal, relationship in the numbers. You want that relationship to continue to be meaningful or useful. So let me give you an example. Let's say I have the size of the car. The size of the car, of course, I can write it as a number. There is a bigger, there is smaller cars. It makes sense to write it as a number. But if I have a color may not be meaningful. It may not be meaningful to write it as a number. The way that you would do that, if you want to proceed and write things as a numeric vector, you would use something called one-hot encoding, which is basically I take all of the colors I'm considering. Let's say I have 10 colors in mind, and I would just put a binary number. Is it black? If it is black, within the column corresponding to the black color, I'll put 1 and everything else is 0. If it is red, I'll put 1 under the column red and everything is 0, and so on. because there is no, I don't want to say black is 1, red is 2, yellow is 3, and so on, because there is no ordinal relationship between the colors. It does not make sense to do that. Now, the downside, if you go with this one-hot encoding way, is the dimensionality of the problem can be much, much larger. It will increase significantly. So it may not work well in that case. So probably that's why things did not work.
So
for categorical features.
go ahead, Dr. Ibrahim.
Yeah, for this type of categorical features, random forest seems to be the best way. I would expect it to do better. Naive Bayes also is the right way, because naive Bayes also works on categorical features. It's not really, you don't need to transform things into numbers in order for it to work.
So it's not a wrong practice to, when I read a paper and I feel like the problem in the paper is similar to my problem, is to use the wisdom of the author, since he's saying that random forest is the best for this kind of problem. So it's not wrong to just go ahead and commit to a specific algorithm.
It is not wrong if you understand the reasoning behind it. Yes, it's not wrong. Yeah, but we have to be careful that, okay, is it really, do we have the same issue as the author, as that particular paper, or is it a different way? For example, you don't want to just use one paper that mentioned a particular data set and they mentioned that random forest works best. That means that we should use random forest for everything. Of course, that's not reasonable.
But how can I tell from the type of data that data set that he's using in the paper? Will it give me any hint?
Yeah, so in this particular case, as I mentioned, it's categorical, it's tabular data, and most of the features are categorical. Maybe in this particular case, you need to worry about, okay, so if I do that one-hot encoding, would it be problematic or not? You need to worry how big is the data set compared to the dimension. Maybe this is another thing you need to worry about. But if you're not sure, if you're not certain, you're not going to lose if you try.
Okay.
So this is, especially that, I mean, coding it is not that difficult. Everything is almost already available in scikit-learn. You can just call the functions. They are already implemented for you.
Okay, so let's hear from another group, Abdurrahman Al-Bugumi وعوض المالكي ونسيت, I forgot who's the third team member. So Abdurrahman, in your progress report, you mentioned that you have found a good data set. Can you tell us about the quality of the data set and maybe the learning algorithm that you're going to use? And briefly, if you can explain the problem, like in 30 seconds.
Assalamu
alaikum.
Well, when I was a session about how to use Twitter, I found the API.
So you are going to use data from Twitter for what? For solving what?
Analyze the text to use it to perform. I will label them. I will choose from this data set. I will label
so
them
basically,
manually.
if you allow me, Abdurrahman, they want to get data from Twitter and build a model to judge the effectiveness of the coronavirus campaigns, awareness campaign on Twitter. Okay, go ahead, Abdurrahman.
Yes, the tweet that follows the same structure or grammatical structure or the same words of the campaigns, I will consider them as a positive tweet.
Okay.
And things that are not related to the coronavirus or have small impact, I will consider them as a negative or zero. I will most probably use these two classes.
So what does
Dr. Ibrahim, لو تسمح لي, let's hear from Awad also because he raised his hand, and then I will come back to you. Go ahead, Awad. Awad Al-Malki, I think you have a problem with the mic. Yes, you go ahead.
Hello.
ايوه معك.
I have question about the data. When we do the training on the data, we have to remove all the mentions, all the URL, all the emoji. But in the real world, we have all these in the Twitter. So how would these things affect our application?
Can you comment, Awad, on the progress that you have achieved so far in the project very quickly?
Yeah, we look up for some papers that suggested three algorithms. One of them is SVM and LR, and the third one I'm not sure where is it. So the paper is taken 2,000 tweets that was labeled as false or true or unrelated, and 1 million tweets for training and testing.
Okay.
That's what
I
understand
just
from
remember
that.
who's the third team member, Hassan Al-Awad. Sorry, Hassan, I apologize. Hassan, do you want to say anything? حسن
No.
اوكي الله يعطيك العافيه. تفضل دكتور ابراهيم.
Just to to answer the second question first, because it's a quick answer. So if you remove mentions and URLs, you're not going to use them as part of your features when you train a model. It's fine, but of course you're not going to be using them as features later on. So you continue to remove them in the future. So that essentially you still have the same distribution of the data. So okay, so this is regarding Awad's question. So regarding the first question, I still I did not understand how you would classify the tweets. When you say if they are similar to the campaign, you would consider them as positive. Everything else would be negative. What does similar to the campaign mean? And when you say positive and negative, what eventually do you want to achieve? I thought my impression is that you want to do something like sentiment analysis. You want to see whether people are tweeting positively about the campaign or negatively. Is this what you want to do?
عبد الرحمن القمي.
Yes, this is the main idea. Yes.
Okay, so you want to do sentiment analysis on the tweet. You want to see whether people are tweeting positively or negatively. Okay. So,
but is it the right measure to measure the effectiveness of the campaign, to measure whether people are happy about it or not?
Yeah, that's a different. Yes, I agree. That's subject to questions. But at least it's a precise question. If you're gonna say I'm gonna look into the sentiment of the tweets, at least that's a very well defined question. Yeah. So it's good in that sense. You have a well defined scope or objective that you want to achieve. But for sentiment analysis, so there is, I suggest you look into the literature. There is a lot of work that's been done. I'm not sure if there is already implementations that are available. I think there should be already available implementations. But I don't know if there is in Arabic. So that will be an issue. The reason I'm saying this is if there is already implementations of sentiment analysis in Arabic, you don't need to train a model anymore. So you can just apply those models on the tweets, and you just do analysis in the sense that you show, okay, how sentiment has changed over time, but you don't need to train a model because it has already been trained for you. You see why you understand why this might be available already, because sentiment need not be related to coronavirus. There are certain positive words, negative words that might be available elsewhere. So you can build a model based on a bigger data set and then just use it for this application. You don't need to train a model for this.
So clearly they need to dig more into the literature.
Yeah.
I found, but in English. Sentimental.
كيف؟ تفضل عبد الرحمن.
Yeah,
I
that's
thought the sentence code in English, but I
yeah.
didn't think I found in Arabic.
Okay. Yeah, that's as I mentioned. I don't know if there is in Arabic. Yeah. In that
But
case, you might.
it's worthwhile to have the model in Arabic also. So this is
Yes.
yeah, it's part of their project.
It's a good thing. Yes.
Okay.
But so one of the things you need to worry about is how to stem the words in Arabic. Visual stemming, you know what stemming is? Stemming, basically you extract the root of the word. Okay.
Oh yes.
Yeah, this is something because you want to train the model based on the root of the word, not based on the conjugations of the word. Okay. يعني for example, to say if someone says in Arabic سعيد مثلا, as an example, it's the same as when you say يسعدني, أنا سعيد or يسعدني. It's the same thing. So the root is, yeah, they have the same root, سعد, and you want to use that. There is a stemmer in Arabic, in the package NLTK, Natural Language Toolkit, in Python. There is, يعني look it up, look for Arabic stemmer in NLTK. There is one already available. You can use it.
Okay.
Yeah, so this is something you should do.
Okay, the third group that I would like to call on is Muhannad, Bassam, Muhammad al-Rashid. They are doing something related to prediction the stock market. Shabab, can somebody give us like a quick idea about the progress you have achieved so far? Maybe Muhannad? Or Muhammad al-Rashid, if he's around. Bassam?
Assalamu alaikum.
Salam
We
alaikum.
collect the data from Yahoo Finance and also from Google's search engine by search for the stock, and also we read some papers about the subject.
Okay.
So the objective here is not really to beat the market and make a prediction. It's really about building a model and maybe build a service around it, like educational service, like you يعني محفظة افتراضية. Okay.
Okay.
Now, what is the recommended approach to this problem, like in terms of algorithm and building the data set?
Well, as I mentioned earlier, I think we talked about this also a couple of weeks ago. Yeah, so if you want to predict the future of the stock market, this is going to be very challenging. As I mentioned last time, there is this efficient market hypothesis. It's very difficult to predict the future of efficient markets like the stock market. So, but if you want to do something else, I'm not sure exactly what needs to be done. If it's more of visualization and reporting, yeah, that should be straightforward. As you mentioned, the data, there is Yahoo Finance has, you can download the data from Yahoo. They have the data available. Maybe one of the things that you can do is to see if the stock market can be correlated with other financial indicators, like so the price of gold, the price of oil, the exchange rates. Maybe this is one of the things you can do, is to see if they are correlated.
Do you have any recommendation for how they should scrape the web? How do they get the data and construct and clean it up?
In Yahoo, you can just download it. You just, if you go to Yahoo Finance, you mention the indicator that you want. You specify the dates, the date range, and you just download manually. So you download the big history manually, and then you just build a model based on that.
Okay.
Other than that, there is. I'm not sure about finance, but usually some companies, they provide APIs. So, but usually I think they are paid service. So but you just call them from Python. You have APIs. You call and you retrieve the data.
Okay, I will go back to Abdullah. So their project is to build a model to estimate the cost of second-hand cars, but the data set they have right now is for the US market. And one of their tasks is to somehow use the model to predict the cost of car inside the Saudi market. So how
Okay.
do they transfer the learning from one model to another model?
Yeah, this is transfer learning. Yeah, as you mentioned. So there is a field called transfer learning that looks into this. Yeah. So usually, okay, so it's a bit. So if they're going to be using random forest, I don't know how in random forest you would do the transfer learning. But if they were going to use neural networks, it's easy. It's just straightforward to do transfer learning in neural networks. You train a model based on this, say, the US market. I will have now a big neural network with weights already trained. Now I take a smaller data set about the Saudi market, doesn't have to be big, and I fine tune the model on that smaller data set. So I train from, okay, they call it fine tuning. I fine tune the model on the smaller data set. With the hope that the original model in the trained on the US has learned some useful features that can be used in the Saudi market. But for random forests, I'm not sure how to. Maybe I'll let me think about this. Or and they can also look it up. Transfer learning, random forest. They might find some papers that discuss how to do this.
Actually, yeah, he just remember that the fourth technique is artificial neural network. So it's on their list of possible algorithms.
Okay.
So since it is much easier to do it with artificial network, we would recommend that you look into this, yeah, Shabab.
Yeah.
But how do you fit the fine tuning in the workflow that you showed us at the beginning of the presentation?
Yeah.
Is it in
So
the validation?
No. So you take your model. So now you train based on the US data, right? And you're done. So your model is finished. The same model now you train it from the solution you obtained originally. So I obtained now a solution with weights or everything. I just train from that initial point on the new data set. So the weights are going to be changed, but hopefully they will change slightly to reflect the Saudi market. But still, most of the structure is already there in the neural network. Does not need to be retrained.
Should we collect some data for the Saudi market? And
Yes.
this, okay.
But
okay.
but the benefit here of transfer learning is that for the Saudi market, you only need a few smaller data sets compared to the US market. You train on one distribution and then you fine tune it on another data set, on another distribution. But you don't need as many examples as you needed before.
So Abdullah is asking, how do you suggest that we collect the data for the Saudi market, since there are no like website that we can fetch the data from them?
Yeah, this is a difficult question. I don't honestly know. I haven't thought about this. Yeah.
Okay.
But they should if they want to. Maybe they might be lucky. I mean, in any case, even if they want to, even if they don't want to fine tune on the Saudi market, they before they make a claim that it will work for the Saudi market, they need to test it. To test it, they
Yes.
will need data.
That's my next question. How do they do the testing? How do they run the experiment and design the experiment to validate that this is good for the Saudi market?
Yeah, they will need the test data for the Saudi market.
Okay.
Yeah.
So this is something they cannot escape. They have to have test data for specific Saudi market.
Yes. Otherwise, they cannot make a claim that it works on the Saudi market. Without testing it, they cannot make a claim.
Okay. Type, yeah, Shabab, we have reached the end of the webinar. This is your last chance to ask your question. If you have any question for today, raise your hand, please. عوض اتفضل.
Okay.
It's a follow-up on the question I asked. Hello?
Yes.
ايوه معك تفضل.
تفضل.
Yeah. So if I want to use my results on in real world applications, so I have to do like a program to scrape all these emojis or mentions to take the to see the result of my work.
Yeah, it depends. Right? Yeah, it depends on how you want it. So you want to build a classifier based on tweets. If within your training data you want to remove, I'm not saying you should. I'm saying if you want to remove emojis, even though emojis is a good indicator, might be a good indicator for sentiment, maybe you should not remove it. But if you want to remove it, and then you want to apply it, you should continue to remove in the future. Or maybe in your case, you might already start with the data set already in mind, it's already available, and all of these are already stripped out. In that case, you should continue to strip them out before you deploy the model.
The problem is with the mentions and URLs. It's different every time they use the, and from one to one, it's different, totally different.
Yeah, that's why mentions and URLs you should remove them. It makes sense to remove mentions and URLs, but maybe not emojis.
اوكي
Yeah,
طيب
thank you.
تقي تفضل. تقي العجمي. تقي.
السلام عليكم.
السلام ورحمة الله.
فكرتنا في البروجكت ان نبني برنامج بحيث انه يكون يصنف يبحث عن الاشخاص من حيث الاسم، مثلا نكتب له اسم الشخص ويدور ان الفيس اللي له يتعامل مع الايمجز ويسوي لنا كلاسيفاينج للايج بعد. فمشكلتنا اللي واجهناها حاليا ان نسوي ايج كلاسيفاير.
طيب
فوش تنصحنا كيف نبدي؟
طيب أنا I wouldn't recommend يعني إنك you build you explore this لأن it can be a sensitive subject. I'm thinking to build a classifier to classify images based on faces, it can be a bit sensitive. Well, there is now a lot of discussion about the use of these types of applications. Classifying people in general is not really recommended. It's very sensitive. I wouldn't recommend it.
هما المشكلة إنه they are at a stage they cannot go back. They will have to continue the project.
Yeah.
Okay, we found a nice solution a little bit, which is classifying age, like for example, classifying people from 0 to up to 25 years, and then from 25 years up to 50 years, and then from 50 years until 100 years.
Okay, so 3 classes.
Yes.
Okay.
So that will make it a little easy for us to do it.
طيب بس in your case you're going to be using which classifier? You should use you're going to be using neural networks, right? Convolutional.
Yes. And neural network, yes.
Yes. Okay.
So do you have a recommended paper that will help us?
Okay, okay, so I don't think maybe you don't need to go. You should look into standard architectures in neural networks. And there is for image classification, there is standard neural network architectures that you can use, like VGG. Maybe, for example, you could try VGG architecture. It's already, I think it's available. You can begin with it. It will give you a good accuracy. There is ResNet architectures you should try. Yani you go with the standard architecture, and in neural networks you will need to build. You will need to choose the number of layers, how many weights, how many filters you will use in every layer, and so on. This can be a bit time-consuming. There is a lot of options. Yani you put regularization in every layer, dropout, and patch normalization, and so on. You don't need to do that. My suggestion is you use a standard architecture that's already known to work well for image classification, and you train on that standard architecture. When you could try is VGG.
Okay.
طيب في باقي عندك أسئلة تقي؟
Okay, thank you.
You're welcome. طيب في سؤال هنا من عبد الله شيخ ويا لأنه يقول عبد الله if the trained data contain around 10k the training data contain around 10k can the test data for the Saudi market be around 1k?
It will depend, as I mentioned. So usually, so you're talking about, okay, you have the training data is 10,000 for the US market, right?
Yes.
انا هذه بقصدها معليش يعني مداخله انا عبد الله
تفضل
طبعاً.
عبد الله.
اي هذا اقصدها لما نجي في النهايه اسوي ترانسفير ليرنينج للموديل اللي عندي انه بس I want to relate it to study market.
Yes.
So how big the data should I يعني collect to
Yes.
relate this problem to the market?
Yeah. Yes. Not ما في يعني there is no straightforward answer. If you do, that's what I'm saying. يعني usually, so okay, so you have 10,000 examples from the US market. You build a neural network model based on them. Then you fine tune on 1,000 examples of the Saudi market. But after you do the fine tuning, we need to also to test eventually to report the test accuracy. So we need another subset of the data for reporting test accuracy, right? Yeah. So how big should the training data in the Saudi market be? This is not easy to answer. And it depends on many things. The best thing to try is to see and to collect as many as you can and see how much accuracy you will get. But keep in mind, you will need test data. And غير the training data of the Saudi market, you will also need test data. And this test data needs to be sufficiently large to come up with a good measure, يعني a few hundreds of examples maybe, to test, to report accuracy.
Actually, this will take us to the second question from the same team member, Ye. He's saying that, okay, when should I stop? When do I know that my algorithm and my model, they are working?
Okay, so usually in real life applications, I have an accuracy in mind I want to achieve. Before I deploy the application, I have a minimum acceptable level of accuracy. You should have something in mind. If you don't have something in mind, you can ask yourself, okay, what would be the random guessing? What would be the accuracy if someone were to just guess at random? And then you would say, okay, how much am I doing better than random guessing? See what I mean? Yeah, for example, if I'm doing binary classification, random guessing, I would get it 50% of the time. Maybe, okay, I'm just going to say that I got 70% accuracy, which is much better than random guessing. But if I were to deploy an application in practice, I should have a minimum acceptable level of accuracy in mind before I decide to deploy it.
Yeah, does that answer your question? طيب مهتدي go ahead.
السلام عليكم.
السلام ورحمة الله. ارفع صوتك يا مهتدي.
We have kind of a different problem than our colleagues. So our project is to
قرب المايك من فمك يا مهتدي.
I think it's close enough. Okay, I will change the.
تفضل.
Better now?
اوكي ماشي الحال ارفع صوتك بس عشان نسمعك.
Okay. So our project is to reassemble a letter from random scatters. We basically write a letter on a paper and cut it apart. So our job is to reconstruct the origin letter. So my question is, how can I train such model, or where can we start from?
Okay, so you have portions of the letter, or they are in random order. You want to know the correct order.
Yes, they reconstruct the letter and the letter like into its original form.
Yeah, so and I personally I haven't really done something similar to this, and I haven't seen
They
something.
have framed the problem as a puzzle, jigsaw puzzle problem, and they're looking into the literature on how they can solve this jigsaw puzzle problem.
Yeah, jigsaw puzzle. There is so you're talking about essentially search algorithms in AI, the A* search algorithms and similar ones. And there is if you formulate it as a search problem, you should look up A*. This is the de facto standard algorithm in search in AI. But there is some other additional. There's something called constraint satisfaction problems. This might be, it depends, of course, on how you formulate the problem. Do you have constraints on how you search or not? But they might be useful to you. But machine learning, or to use a machine learning approach, means that I would have these different pieces together, and I would have the correct answer. And I would have many of these examples, and then I build a model that can try to get this. Personally, I haven't done something similar. I don't really know. يعني.
طيب ها مهتدي في do you still have any other question?
No.
Okay, thank you. طيب, I think that's it. We are like about 15 minutes beyond our time. So on behalf of the chairman of the computer engineering department, the faculty members, and all the students, I would like to thank Dr. Ibraheem for this lovely and interesting and informative presentation. And also want to thank the students for their who are with us today for their dedication to the course and the project. And as I mentioned at the beginning, we're going to meet again with Dr. Ibraheem in a special mentoring session for the student on their projects. So thank you, Dr. Ibraheem.